Hello and welcome to this video about determinant proofs. In this video we'll prove that if we transform a region by a linear transformation T, then its volume will increase by the determinant of the matrix corresponding to T. I'll just develop the statement of this proof more slowly. So we'll define a region in n-dimensional space and call it S. We'll illustrate it here with a circle in two-dimensional space, a circle being the best irregular figure. Then we'll set T to be a linear transformation. T will transform this circle region into this ellipse that's leaning to one side, and we'll call this new region TS, which is T applied to S. And we'll set A to be the matrix corresponding to T, so that we can use this matrix to multiply on the left by a vector rather than be applied to it like a function. We'll define a volume function vol, which returns the volume of any given region. It can be any dimensional volume. In this example, it's an area which is an n-dimensional volume. And so this formula is true, that the volume of one of these regions is the volume of the other region multiplied by the determinant of A. So now to prove this theorem, we'll split the first region up into n-dimensional cubes and get the total area of these n cubes, and add them together, which should give us an approximation for the n-dimensional volume of the first region S. Our illustrated example is working with two-dimensional space, and we'll get the area of all these n cubes. We'll let the n volume of one of these tiny n cubes be equal to the volume of epsilon, which is normally set to be equal to a very tiny quantity to be used in calculus, and then the sum of all these little cubes will be set equal to the total volume of the region. In this case, these tiny little things will be squares, and we'll add up their tiny little areas. Then we'll apply the function t to these n cubes to get the volume of the second region, TS. So I'll just shift everything up the screen to make some more room. Here's an example of how we'll use these tiny cubes to find the volume. We'll fill the region with cubes and only count the cubes that are entirely within the region, and then colour them green. The rest of the cubes that are a bit outside the region are coloured in yellow. Looking at our example, these cubes are squares inside a circle, and the squares completely inside the circle are green, while the squares that aren't completely inside the circle and are sticking out a bit are coloured yellow. After we apply the transformation T to this region, then the region will distort, and the cubes will distort too. The tiny cubes will distort into tiny little parallelepipeds. But if you look carefully, then you can see that each of these tiny parallelepipeds can be mapped to a cube and back again. So the number of these tiny things in each region will be the same. The volumes of these two green regions will be related by the volume of the second green region being the volume of the first green region multiplied by the determinant of matrix A. This matrix corresponds to the linear transformation T. So now to start a new page. This is how each of the tiny parallelepipeds will be related to the n-dimensional cubes, because we've proven it in a past theorem. We'll multiply each side of this equation by the number of these tiny cubes and parallelepipeds, which will be the same, and this number will be m. We could then limit m to infinity so as to get the exact volume of each region. And this will be as simple as placing the limit sign in front of the equation like this. I think I can get away with putting it in front of the left-hand side equation, and so it'll work with both sides of this equation. So let's take a look at what this would look like. If we make m larger, say increase it from 32 cubes to 88 cubes, then these cubes would be smaller, but they'd better approximate the volumes of both sides. If m were 1 billion, it could approximate the volume to 6 decimal places. As we use this limit for the second volume of the sum of distorted cubes, then it'll be exactly equal to the volume of the second region. We can then combine these equations to get this equation, which is what we're trying to prove. So we've proven this theorem. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.